Hello, we will continue our discussion on classical molecular dynamic simulations. Uh, in the last lecture, you were introduced to several types of files. Some of those files you can edit using your VI editor. Some of the files you cannot edit because they are binary files. The examples of binary files are your TPR file, TRR file and XTC file. Now, why we use binary files instead of regular ASCII files is because binary files occupy much less space on the hard disk than your text files. Text files or ASCII file, they take a lot of space. So, and you know, space on the computer becomes a very primary issue because your trajectories are long, lakhs of steps are carried out and you cannot save all that information if it is in the text format. Okay, so before we continue our discussion on simulation on water today, we will show you some videos on molecular dynamic simulations. Can you start the first video please?
Yeah, so this is a video of NaCl in pure water. The green one is chloride and the purple one is Na+. This is a short video.
Okay. So then you can show some other video.
Yeah, sure.
So you will see that in classical molecular dynamics, all the molecules are represented as some sites, interacting sites. If it is a water simulation, the water is represented by 3 sites, that is 1 site for oxygen and 2 sites for water. Okay. So now this is for a supercritical fluid.
Yeah, this is for a supercritical fluid and this is pure water.
That is a simulation for pure water.
Yeah.
You will see that the white objects are hydrogens and the red object is the oxygen. Now why don't we see a simulation on a more complex system?
Yeah, we can show them representation of a micellar system.
So we call it classical molecular dynamics because all the equations of motions are all classical, that is based on a Newtonian equation of motion. Whereas in a quantum mechanical simulation, it will be based on Schrodinger equation or Dirac equation or more complex versions of that. So since you have seen the video, you can see that whatever simulations are done, you can actually physically see on the screen. And of course, remember that these are all simulations. Simulations are not 100% reality because all simulations are based on some model potentials, models of algorithms. So it is not a 100% reality, but it gives us a fairly good knowledge of what reality is about. So this is simulation
This is for a micellar system. It is being aggregated in the solution.
Okay.
This is a more complex system than water or methanol or argon.
Okay. So now what we will do, once you have seen that, now we will go back rather to see what are the files that you need for water simulation. Okay. So today we will be discussing how to create input files for water so that you can do molecular dynamics of water. Okay. So we again begin with your PDB files, topology files. So let us start with simulation for water.
So for molecular dynamic simulations of water, we need the input file which are required is the structure file of water, that is water.pdb. Then we require topology file, that is wherein the force field parameter of water is included. Then we need the MDP file, which is the molecular dynamics parameter file. We need 2 MDP file, one is the energy minimization MDP file and one is for the full molecular dynamics.
So can you comment on where these files are available?
These files are available in the GROMACS site itself, and also in the manual GROMACS. In the manual of GROMACS, the format is given, like what should be the format of a topology file, of a molecular dynamics parameter file, and PDB file is you can create a PDB file using Gauss View, Avogadro, or it is available free of cost from Automated Topology Builder or RSCB Protein Data Bank site.
Or if I know the structure of the file, I can create it manually also.
Yeah, but you can create it manually for a simple molecule, but when it becomes more complicated, then it's easier for us to download it from somewhere or to create it and then optimize the geometry and then use it.
Okay, yeah.
And to generate…
But you did not say about the INP file.
Yeah, INP file will come later when we discuss about the generation of initial configuration.
Okay.
So to generate initial configuration, we will use the help of the software PackMol, which is a free software. And first we have to log into our machine or server, and then we have to go to the directory PackMol using the command cd. And we'll have the file water.pdb, which we can view using the command vi. So vi water.pdb, this is the PDB file of water.
Okay. So
Where
let us see this very carefully because it gives
Yeah.
information about all the details.
yeah, so the last three columns represent the coordinate of x, y and z axis of three site of water, since water is three site molecule, one is oxygen and two is hydrogen. So OW, HW1 and HW2 are the site of water molecule, and the last three columns are the coordinate of x, y and z axis.
And the first three lines, that is header, water, compound, source,
Yeah.
that is common for all PDB
That is
files?
common for all PDB file.
So, and earlier some files had a blank line, is that allowed or no?
Yeah, that is allowed. Blank line doesn't mean anything. Like
Okay,
you
because-
can either write something or you cannot write something.
Because you can see now the GROMAC structure is so built that it is very, very flexible as far as data is concerned.
Yeah.
Whereas when we wrote our own programs earlier, you see that even if there is a blank line, it will make a big mess. Because a blank line will mean either zeros or nothing. So, if in the program that you write, unless such flexibility is there, you have to be very, very careful about the data structure.
Exactly.
Because one dot or one single digit, it can mess up the whole thing.
Yes.
Okay, so it is nice that they have worked on a fairly good structure, and I would like to comment on those XYZ coordinates. So before that, what is that 1, 2, 3 on the left?
1, 2, 3 is the atom number.
Okay.
Like there are 3 atoms in water, so
Okay.
it's 1, 2, 3.
Okay.
And SOL is the residue name for water.
Okay.
And
So instead of SOL, can I call it POL?
but then POL has to be same throughout.
Okay.
Like if you use POL in water.pdb,
Okay.
so you have to use the same residue name in say topology file or in the ITP file. Or
Everywhere.
you have to use the same
Okay.
residue name. Residue name is user defined,
Right.
whatever
But-
the user defines.
But whenever other people are making PDB files, they are using SOL as a common feature.
Yeah, SOL is a common feature.
Okay.
And,
what are the next lines? We have 1, 2, 3.
Yeah, connect 1, 3 means that the bond oxygen and hydrogen is connected, right?
Okay.
1 and 3 and 1 and 2.
Okay.
So that is a bond connectivity which is
Okay.
represented. And the last line where connect 2, 1, 3, it's a bond angle connectivity.
Okay. So that means you don't have to give the actual bond angle. The computer knows how to calculate the angle since
Yeah.
you say 1, 2, 3 have an angle.
The actual bond angle and bond length, everything you have to specify in the topology file or in an ITP file.
No,
But in a PDB file, you don't have to actually write the bond angle and bond length.
But I would say that information is already contained in the coordinates.
Yeah, you can
Because
calculate the
suppose-
bond angle and bond
so
length as
that
well.
we will leave it as an exercise. Now you know that 0, 0, 0 is the coordinate of oxygen atom.
Yes.
And the second one minus 0.560, minus 0.410 and minus 0.750, these are the x, y, z coordinates of the first hydrogen.
Yes.
Okay, so if you treat it as a vector, now treat this minus 0.50 as an x axis, next one as y, third one as z, it is like xi plus yj plus
Plus
zk.
zk.
Now you can calculate the length of this, the length will be x square plus y square plus z square square root. Now since the oxygen is at the center, this length will be just the OH bond length.
Yes.
Okay. So similarly the second one, you see the second one is slightly different from the first, that is the bond length between oxygen and hydrogen.
Yes.
So I will urge you to calculate these bond lengths. Now suppose you want the distance between two hydrogen atoms. You can calculate from here because you have x1, y1, z1, x2, y2, z2. So if these are the two coordinates, the distance between them is x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square root of that. So that will give you the
Bond length
between
two hydrogen.
two hydrogens. And if you want a bond angle, you have the first vector for OH,
And
second vector for OH2, OH1, OH2. Just take a dot product, this will give you cos theta, and cos inverse of that will give
us
you
the
the
bond
bond length. So, and make sure you have these unit vectors, because if it is not a unit vector, you will have a problem. So what you do, OH1, OH2, take unit vectors in those directions, then take the dot product, cos inverse, then you will get the
bond angle.
bond angle. Okay. So therefore, whenever you see these coordinates, I urge you to make it a habit that you check these things, because ultimately the result you get, you are responsible for it. So you have to make sure that the coordinates are correct.
And this is the basic input file. So it
and
has
in
to be
case something is wrong here, then everything will be wrong.
Yes.
So in fact, you will be using several molecules. No, maybe you have a mixture of alcohol and water.
Yeah.
Alcohol, you can use many solvent molecules. So make sure that whatever your PDB file is there, you check the bond lengths and bond angles, at least one or two, so that you know that it's a reasonable thing.
Yes.
And also now this, which kind of a model for water is it? Is it SPC?
This is SPC.
No. And furthermore, there are many models of water with different bond lengths, different bond angles. So we will be doing with SPC water. So in your home assignments, maybe we will ask them to do for some other model of water.
Yeah, there is tip 3P, tip 4P,
Okay.
4
So-
site or 5 site maybe.
Okay, so
they
there are
can,
different models with different
continue
sites.
with.
So as you go along, you practice with other models in your
Yeah.
results. Yeah, you can. Any other questions on this now? Things are okay?
No, thanks.
Okay, yeah.
So now we have the water.pdb file, and now we have to put it in a box.
Okay.
So we have to define the box length and how many number of water molecules are to be put in, what is the name of output file. So all these are contained in the INP file.
Okay.
INP file is an input in PACMOL.
Okay.
So you can open the file water.inp using the command vi. So vi water.inp will give you a file like this. So
But this one, is it not created by us?
you can create it or you can download it also.
No, but-
like initially if someone is a beginner, they don't know what is the format of an INP file.
Right.
So they can go to the site of PACMOL
Okay.
where there are input examples for
Okay.
water urea mixture, for bilayer, for single water molecule. So they can download the INP file and PDB file from there as a beginner, and
Okay.
it's free of cost.
But now
So
for
they will-
water, is there only one INP file or there are many?
The INP file format for water or for any molecule is the same. You
Okay.
have to have a tolerance, you have to define the minimum distance between two atom or molecule,
Right.
you have to define the file type, you have to give an output file name.
So what is the meaning of tolerance 2 here?
Tolerance 2 is the distance between two molecule is less than or greater than 2 angstrom or minimum 2 angstrom.
Okay.
That is user defined. You can give 2,
So
3.
I would consider that 2 is very small between two water molecules.
You can give
I would
3
like
as
to
well.
give something like 2.8
Yeah,
for example.
that is
Okay.
allowed to give.
So I can change that 2 to 2.5.
Yes, yes,
But I
definitely.
cannot change the next 2 lines.
No, next two line file type has to be PDB because PACMOL in PACMOL the input file format is a PDB file format.
So now
and
you
the
have a-
third line output
Huh.
that is dependent on user, whatever
Okay.
the file name they want to give.
So in this file, the fourth one is a blank line.
Yes.
So can I remove the blank line,
Yeah, you can remove the blank.
or can I
blank
give
line.
5 blank lines?
Yeah, you can give 5 blank line as well. Doesn't matter.
And the one thing that people can change now in this INP file, you have 899 water molecules
Yeah, they can change
and
it.
30 box length.
Yeah.
So I would ask you as an assignment, take 20 as the box length, that is in angstrom, and calculate how many water molecules are there.
Yeah.
So maybe when they do the execution, you can change that 30 to 20 and 899 to some other number.
Some other number. Yeah.
So before we come to the next lecture, please calculate how many molecules are there in a box of 20 by
20
20 by 20. So again now PDB files are all in angstrom
PDB
unit.
file are all in angstrom unit,
So
and
we will have-
whenever we have to use it in GROMACS,
Right.
we have to have in a GRO format,
Correct.
and the unit has to be in nanometer.
Nanometer. So that we will do when we go along. So what is the next file now after this PDB?
So next is structure, where
Okay.
we have to give the PDB file of water or methanol or any other molecule that we are
Okay.
simulating.
Ah.
Number is user defined. You have to first calculate the number according to the box length and density of the
Okay.
molecule.
But that is already done here, no?
Yeah, that is already done here.
Right.
And then inside cube, it means that it's a cubical box. The box length is 30 angstrom. You can have a different box as well.
Okay.
I have taken here cubical box, and then you have to end the structure.
Now, okay, structure and end structure.
Yes.
So now that between inside and cube there is 1 or 2 spaces.
Yes.
Can I make it 3 spaces?
No, because inside and cube, like inside is a separate word and cube is a separate
Right.
word. So there is one space in between.
So I cannot change the space here.
No.
What about that 0, 0, 0 now?
Yeah, that space you can change.
So instead of whatever space given on the
One
screen.
one space is there. 0 point space, 0 point space, 0 point space.
So can I make it 0 point space, 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 0 point space,
Yeah, yeah, you
space,
can
space?
do that.
It doesn't matter. It should be on that line. It
Yeah,
cannot
it
be
should
on
be
the
on
next
that.
line.
No, it cannot be on the
Okay,
next line. It should be
okay.
on that line
Yeah.
itself.
So and in case some of you get an error, you just go back and make sure things are in this order. Okay.
So as I've already said that that is the output file name. This is the input file. This is the number of water molecule, and there is a cubical box of box length 30 angstrom.
Okay.
So now we have to execute PACMOL using this water.inp file.
Okay.
So to do that, we'll use the following command: /PACMOL space less than equal water.inp.
So that means water.inp is an input file.
Yeah.
PACMOL is an executable command.
Yes.
And the result will be stored in some other file name.
Yeah.
Okay.
So the result will be stored in, as it is written there, that solution written to file liquidwater.pdb.
Right.
That is the output file name.
Okay.
And after successful execution, it will show like this in the screen, success, and then the time that it has taken to run the
Okay.
file.
So what is this violation of the constraints? See, you have success,
Yeah.
then final,
Objective function value, then maximum violation of target distance,
Right.
like whatever the tolerance we are giving.
okay,
So what is the violation that they have done? So that is what is written there.
okay,
Maximum violation of target distance. But if the tolerance is less than 2,
Huh.
or if it doesn't satisfy the
okay,
thing, then it won't write the PDB file.
So-
It will say something like the structure is forced to be written in that box
Fine.
length.
Now, so these constraints, are these bond constraints or some other constraints?
Bond constraint, because everything is
Okay.
dependent on the in a polyatomic molecule is dependent on the bond length and bond angle and distance between molecule.
No, but my other question is, what this PACMOL is doing is really packing several molecules in a box,
Yeah.
correct?
And we are giving the distance, like if there is one water molecule, first we are placing it in center, let's say.
Correct.
Then the other water molecule, it is placing 2 angstrom far away from the first one.
Correct.
Then again when it is putting the third one, it is placing it 2 angstrom far away from the second one.
Correct.
So this is the way it is packing the molecules in the system.
So, but the way we used to write our own programs, we just take a molecule and put it somewhere. There is no change of bond length or bond angle.
Yeah, bond length and bond angle won't change here.
Correct, but then still there is a, so what is that constraint? then?
Constraint is the distance between the molecule, because that is the only constraint we are giving, that there, you see, when we were doing argon simulation, we have used tolerance of 3 angstrom.
Correct.
So that is the distance between 2 argon atoms should be minimum 3 angstrom. It cannot be less than 3.
But so here it is allowing some flexibility,
Yeah.
right? Because if you don't allow for this flexibility, it is sometimes very difficult to put all the molecules in a
Yeah.
box. Okay, so now you see that although there are some constraints here, that is maybe some lengths are less than expected, when you do energy minimization, automatically this will be
This
pushed
will-
away.
Yeah.
Okay, and what is the last line? Running time?
Running
0.6
time
seconds?
is 0.6 seconds.
Right.
It took 0.6 seconds to execute the.
Okay,
Packmol.
so now since the last line says some line is there, that is the working directory, isn't it?
Yeah, that is PACMOL directory.
So we are still in PACMOL
PACMOL.
directory.
Now we have to copy the file liquidwater.pdb
Right.
in the directory where we want to do simulation of water. So for
Okay.
that, first we have to create a directory mkdir water
Okay.
outside the PACMOL directory, and then we will copy the file liquidwater.pdb to that directory.
So now there is also, is there not a GROMACS directory where all the things are uploaded?
Uploaded, but you still there is a GROMACS directory, because unless you have GROMACS directory, you cannot run the command of GROMACS.
Right.
But though there is a GROMACS directory, you have to create a directory for water or for
Right.
argon.
So all these commands like G_RDF, all that, they are all in GROMACS directory?
They are all in GROMACS directory, because if they are not there in the directory, you cannot
Nothing will
run.
happen.
Nothing will happen.
So
exactly.
whenever, now you are putting all these files in water directory, you will
Yeah.
create one.
Yeah,
So when you run the final MD run,
yeah.
do you run it from water directory or do you run it, or,
We run it from water directory, because water directory is anyways in the GROMACS directory.
okay.
So you have created that directory.
So this water directory is a subdirectory of GROMACS?
Yeah, it is a subdirectory of GROMACS.
Okay. So then that is how you make sure that everything that is there in GROMACS will be known in a subdirectory of GROMACS.
Yes. Or suppose you have downloaded GROMACS in your documents or downloads directory.
Okay.
So it is not required that you have to have water directory in the GROMACS directory.
Right.
Since GROMACS is installed in downloads,
Correct.
so you can create a directory in download folder
Okay.
as well.
Or let us say I create my directory in some other drive.
Yeah.
I can always give a path wherever
Yeah.
the GROMACS files are.
Yeah. So for that you need to have a script file.
Correct. So which
And-
means it will be more and more complicated if your files are kept
Yeah.
all over the place.
Yeah.
So it is best to have all subdirectories inside the GROMACS.
Yeah, because
Right?
that will be easier
Then-
for the
right.
user to handle
Correct,
it.
correct. Okay.
So now once we have the water.pdb file, so we will convert it into a GRO file
Okay.
to use it in GROMACS.
Okay.
And to do that, first we will copy liquidwater.pdb from PACMOL to water directory,
Okay.
and then we'll give the command to copy this cp liquidwater.pdb to water. And
Okay,
then
but Which means a water directory has already been created.
Yeah.
We didn't have that command here.
No, for
Okay.
creating water directory,
You
we
just
just
say
have to use
mkdir.
mkdir command.
Right.
Right, and now to convert liquidwater.pdb to .gro file, we'll use the following command.
In that command, liquidwater.pdb ...
Yeah.
should there be a place after pdb?
No.
Otherwise, it will
Okay, cp space liquidwater.pdb.
right.
Then you have to give. I don't think there has to be a space.
Because if there is no space, the whole thing will be like a path, no? You are copying from one place to another.
Place,
so I
yeah.
think there should be a space.
Okay.
Okay, so it is a good challenge to users. Whatever we give on our screen, when you practice, there will always they say no, there is always a slip between the cup and the lip. So you make sure that whenever there is a problem, you can always send an email.
Yeah.
But by and large, you will be able to, since you have now practice of almost 10 weeks, you will be able to correct these things. Okay. Yeah. So you have copied now to water directory.
Yeah, and now we'll convert the PDB file to a GRO file using the command genbox.
Okay.
So genbox space minus cp, then we have to give the input file, that is liquidwater.pdb, then space minus o, which is the output file, space output file name, that is configuration.gro or conf.gro, then space minus box, then we have to give the box length.
So suppose that minus box 333 is not there, then what will happen?
It won't take, it will just create a GRO file, and then the box length space which we have in GRO file, it will be 000 since we are not specifying any box length.
So if I don't give the last line,
Yeah.
I have to go back to the GRO file,
And then you have to edit it.
and give that probably in the last line.
Yeah, in the last line.
Okay, so now
But best is to write the box length here itself.
But now this is still, now it has already gone into nanometers.
Yeah, it has gone into nanometer because it is a GRO file,
Right.
and in GROMACS the distance unit has to be in nanometer.
Now what is that minus CP stand for in GenBox?
Minus CP is the input file. It is a flag for specifying the PDB file,
Okay.
and minus O is a flag for output file.
So it has to be minus CP, not just minus C.
No, not just minus C is an input file for GRO file.
Okay.
When we will use this conf.gro as an input for say energy minimization or full molecular dynamic simulation, then we will use minus C space conf.gro. Minus C is a flag for as an input for GRO file.
Okay.
But
so
here
which means they have to be very careful what options are given.
Yeah.
Okay.
If they just type genbox space minus h, h is the help command, they will know what is the flag required for an input file or for an output file.
And all the flags will be listed there.
Yeah, all the flags, and there it will be written that this is an input file option, this is an output file option.
So for which command, which is an input file?
Yeah, all of them will be written there.
But minus O is always for output.
Minus O is always for output.
Okay. So and conf.gro, this is a file, again it's a text file which can be edited.
Yeah, it's a text file, it can be edited.
Okay.
For sure. So something like this will occur after we type the genbox command.
So you have basically edited the GRO file now to show this, or it's just the output on the screen?
It's the output on the screen. Now I'll show the GRO file.
No, go back to the output, let us
Yeah.
see. So what are all these things now?
So it's like it is reading the solute configuration which is built with PACMOL, which contain this many number of atom.
Okay.
Because there are 899 water molecules, so 899 into 3, so there will be that
so
much.
many atoms.
Yeah. So they are initializing the van der Waals distance,
Right.
and then the total volume is 27 nanometer cubes since the box length is 3 nanometer.
Right.
So this is the density 996 gram per liter, and total number of solvent molecule is 899. So this is the thing that will be displayed. Basically all the input parameters which we are specifying.
Okay.
And this is the GRO file.
Okay.
So sol, it is a residue name, then OW, HW1, HW2, this is the atom name, and the last 3 line are the coordinate of XYZ axis in nanometer.
Okay. So now you have created coordinates of 2697 atoms.
Yes.
That means 899 molecules.
Yes.
So and your first column will give the site number.
Yes.
So it will go from 1 to 2697.
Yes, it will go from 1. No, it will first column is the solvent. No, solvent residue name. So first you see there is one sol, one sol, one sol. So one
first
solvent is first
is one.
molecule.
Right.
So it has 3 sites. So there is 3 one solvent, one solvent, one solvent.
So 1, 2,
It goes-
3 will correspond to one sol, one sol, one sol.
Yes,
Those
then-
are OW, HW1, HW2.
Those are the index number
Correct.
of the first water molecule.
Correct, okay,
Then 4, 5, 6 is the index number of the second water molecule.
okay.
So this goes this way.
Right. So which means the left column, 1 will be written 899 times.
Yes.
Sorry, no.
Yeah, one will be 1 to 899.
Right.
The third column, which is 1, 2, 3, 4, it will come 2697
Yeah.
times because
Third column is the atom or site number.
It is here.
And first column is the molecule number.
Yes, it
So
is the
it will-
residue number.
So by molecule you mean the residue.
Yeah.
Okay. So but do they always call all molecules as residues?
Yeah, because in Gromax molecules are called as residue or residue number because
So to me that residue looks like some precipitate and all that.
no.
Huh?
Because in Gromax this is a general practice to use it.
Okay. And the extreme 3 columns on the right are the coordinates.
Yeah, they are the coordinates of x, y, z axis and nanometer for
Right.
each site, for each
So
atom.
now since when we started the first coordinate was 0, 0, 0 oxygen
Yeah.
and 2 hydrogens.
Yeah.
Now these have all changed.
Yeah.
So which means once you run PACMOL, nothing may remain in the original site.
No.
Okay. So for users, you may just take any water molecule and calculate the length between oxygen and hydrogen
Yeah.
1 and oxygen and hydrogen 2. Make sure those bond distances are the same as the original one.
Yeah, I have already given it as an assignment to calculate the
Okay.
OH bond distance between
Correct.
first and fourth molecule
Right.
or like that.
And if you have a lot of time on some evening, you can go to this coordinate file and calculate these distances. Make sure your water molecules are the correct geometry.
It will be a large work to do because
but-
there are 899 water molecules.
But they can
It
also
will take-
no. Now you see what you can do. You have now learned Fortran.
Yeah,
You can read this as an input file.
yeah.
Correct.
And then it can
Then
write
calculate. You can write a program to calculate the distances between all OH bonds
Yeah, and
and
it
see
will-
how many bonds are
One
exactly
angstrom.
and what is the average bond length in your water
Yeah.
and standard deviation. Lots of this data you can use as an input file for lot of calculations using your earlier programs. If necessary, I will put that on a website. We will conclude this lecture right now. And what will we do next time?
Next we'll see the topology file
Correct.
of water and we'll proceed to the
Right.
energy
So
minimization.
in the next lecture, we will do the topology file and the remaining step and finally go to the final calculation on water.
Yeah.
Okay. Yeah. Thank you. We will conclude this lecture now and continue with this in the next class.